Good evening, everyone.
Good evening.
There are a couple kind of announcements or things I wanted to make you aware of. I have noticed that a lot of people want to go into career medicine because they think that's what you will do if you want to help people. Not like a bad thing, but like that's like if you're like want to do science and you want to help people, you go in a career in medicine, either nursing or doctor or whatever it is.
Job stability.
There's a lot of really good things about being a nurse, and so I'm not going to talk down upon any of the careers.
Look, we'll call there's a whole room full.
But I also, last spring...
We probably got needles from clinical in our bag, so you better...
I already got stabbed by one today.
You should have let me do it.
I wanted to start a seminar series that talks about additional careers that are available that are interesting and related to STEM fields, to science and medicine mostly. So last spring I started up a seminar series called Friends of Medicine. We had 10 speakers come that talked about biomedical research and different ways of working in hospitals. This semester, the Dean of the College of Arts, Letters, and Sciences, not your college for most of you, but they decided they wanted to continue the seminar series, so they're inviting a number of speakers that are in related science fields. So the first seminar is October 23rd, which is next Wednesday, right before our class, 4:30 to 6. And the two speakers are on the Dean's Science Council at UA Little Rock. There's Cheryl Avant, who's in, I think, basically the insurance industry, but she's come up through a scientific kind of background. And then Nathaniel Noble, who was in the military, then he got a chemistry degree, and now works for has worked in forensics and works in the Department of Health, I believe. So these are our first two speakers. They're going to be there, and they're going to tell what was their path of getting where they did. It's not as much about what their current jobs are, but it's about how did you get there. And so things from what were stumbling blocks along the way, what were the successes, who was your champion, how did you deal with failures, how did you get to successes, those kinds of things. So that's going to be a seminar series that's happening twice this fall. The second one is November 20th. And that's Dr. Jonathan McGordy, who is an anesthesiologist at UAMS. He is amazing. And he is also in charge of the opioid education division at UAMS. So he does a lot of public outreach with opioid epidemic stuff and training of he's trying to educate people right before they go into surgery about the dangers of taking opioids, even one day less. Can mean this, those kinds of things. And then he's going to be partnered with Christopher Jones, who is the person who runs the Innovation Hub in North Little Rock, who is a PhD in engineering at MIT and has gone a long way around and done education and a whole bunch of stuff related to innovation, and now he runs Innovation Hub. So these are two of the seminars coming up soon that you might be interested in coming to. Another word that helps is free food. So if you are interested, there was an email that just went out university-wide, I believe, in the last couple of days. If it hasn't, I will resend it. But there's a place to RSVP, ualr.edu/cals/Friends of Science and Medicine, FOSM. So if you're interested at all in those two speakers, and there's a chance afterwards, they're going to talk for 15 minutes each, tell you about their winding story, and then it's Q&A. So you can ask them anything you want. It's a way for us to bring people from the community in that might be resources career-wise, or it might just be interesting to hear how they did it and to how here they might have had a really hard time their freshman semester in chemistry, or when they did this or that course, or whatever it is. So I thought you might be interested.
So that means we gotta take some more science.
Can you go back to this one time?
I'll put this PDF in our Blackboard site somehow. Maybe a discussion post? I don't know. I'll figure out how to get it to you. The second set of pieces of information, office hours. I'm adding an additional office hour tomorrow from 10:30 to 11:30 because a couple students wanted that. And I forgot to add my Friday office hours on here. So my Friday office hours are, let me do it in yellow, white. Friday 1 to 2:30. Also an ETAS 125. So those are my two office hours at the top. And then some of the learning assistants have volunteered to hold study sessions. And so you probably saw those right before the exam. Here's a list of some more. So tomorrow, these are modified hours from what they normally have, 2:30 to 4:30, and then another session from 6 to 8. This is when you can bring in your workshop activity or the class material or your homework, and they can help you kind of work through those and guide you. Saturday, 12 to 2. They're not there for 4 hours. Akia's like, I didn't sign up for that. I think, is it one or both of you involved in that? So Akia is one of the two. Evan is one of the others, and I don't know if there's any other individuals that are also doing that. But they're basically there to support you, and that's really close to where the computer lab or the lab is. It's right around the corner. It's a computer lab. It is chilly. Bring a sweater. And then the last thing is the chemistry department has a talk every Friday, pretty much a seminar, and we bring in different speakers. Usually it's super technical, like stuff that probably wouldn't interest you. I'll just be honest. Sometimes it doesn't even interest me. It's so technical and so in like one field. But this week we have someone coming to talk about nanomedicine, enhancing radiation therapy. So you might be interested in coming to that. It's in this room at 2:30 on Friday.
Do you ever have anyone in the forensics field come into that?
We have not, no. But Dr. Nathaniel Noble, who is talking next Wednesday, has been in the forensics field. So that's one of his pieces of background. But 2 weeks ago, there was someone who was talking about Parkinson's disease and how to use mental models to look at anxiety and irritability and how that relates to some of the biomarkers. So it's a chemistry department thing, so it's always going to have some chemistry focus of it. But he was kind of looking at how we compare those two things. So a lot of doctors from UAMS will come over and talk about their research. So that's 2:30 on Friday in this room, and everyone's welcome to come to that if you'd like. Cassandra? So needy. Okay, as we start the first clicker question, I will do that. Actually, I can just do that right now. Okay, go ahead. So today, we are going to make a lot of progress because we haven't so much the last couple days. Right? There's some really challenging topics we're working on. I wanted to try to get ahead of where you were in lab, and that never happened, right? Because some of these topics are really challenging. So hopefully the pre-class quiz today is merging with the stuff you're working on in lab, and you're starting to kind of see how some of the pieces fit together, and we're going to work on it some more in class today. So this is kind of what we've been doing so far, and we've been working on some of the converting between how heavy something is and how many of them there are, and we've been doing the other way around. And what we're going to add to that today is to look at a balanced equation and figure out how to go from how much of a starting material we have, and then how much product can we possibly make if we use all of that up. What's that? Pre-class quiz.
Okay, I can hear you.
I might be talking wrong. Okay. Let's work on model. Is this model 3 or model 2? Where this image is?
3.
Yeah. Go ahead and open up model 3. This is a color version of the image you have. The colors might help a little bit. You'll notice that these two things at the bottom are color-coded. I want you to answer those questions 10 through 15. Talk through it with someone next to you. And we're going to start thinking about how this idea of conservation of mass applies to more than just our chemistry class.
I'm so medicated right now that I'm a little loopy. I really don't like cement for my eyeballs out. And then it was like,
John Paul, you have a question? What's that? These total activities will have some terminology, but we can make sure that So it's yeah. So what does it mean? Look through the pools and the fluxes and then think about that. So fossil fuels are pulling soil across the atmosphere.
Depression. All it does is just kill the pain.
Once I read the definition.
Actually, oh, it's crying, girl. I'm the worst.
Source for carbon.
Let's answer this question. Wait, when they say pool, they're not talking about a swimming pool, I'm guessing. Pools. They got water? What do they mean pool?
I don't know, but I'm gonna circle everything and
A flux. What's the 7 carbon pools? What's a carbon pool? It stores carbon for a long time. Oh, thank you. It's the atmosphere. Thank you. I thought it was the water. Intermediate and deep ocean.
Is the ocean one?
Oh, that reminds me.
The ocean habitat.
I think it's because I'm wearing my using my history sweatshirt, which makes me like
Let's take another 2 or 3 minutes to try to answer all the questions.
history. They have this display that
It's
shows
not going to be the
you
terminology.
areas and stuff of the surface ocean and the ocean to ocean. Yeah, it's just. I think it's pretty. Empty or into? Empty. But there's some cities that are like that.
you should look at that. Yeah, I think it would be up your alley.
It's on Netflix. Or where?
Hulu? It might be on Netflix, but I think it's on.
We have Netflix and Amazon Prime. What is the largest car? Because it's crust.
Yeah.
My record was 7. I had 7.
That has 100 million.
It's
The PG.
You still let me do it, it wouldn't hurt.
Oh yeah, I had 0 complaints about it.
It wouldn't hurt if I
In fact, I was woke up
It didn't hurt that bad right in when it, it didn't hurt that bad when she did it. It's just really sore now.
did it. Is it one of your students? Well, then what's the point?
I assume it would have hurt if one of my students did it. Would have hurt a lot more.
This is
Raise your hand if you want 1 more minute. Do we want 1 more minute to work on this? Okay, we'll do one more minute.
Wait. No photosynthesis. No, that goes down. Light respiration. Volcanoes.
Nice. You do commercial?
It's definitely easier when it's in color.
Describe the path of carbon to reach the source of the fossil fuel. What?
Make sure you get the next question. So try to do this one so we get the math together.
It burned after a fossil burn.
Because I know that ocean.
With the litter fall.
Alright, let's go ahead and start talking through some of these. The first few questions were to orient us with the diagram, and then we talk about how it relates to what we're doing in class. So can I have a volunteer to point out what are the 7 carbon pools and which one's the largest? Go ahead, Andrew.
Alright, the 7 pools are atmosphere, plants, soils, fossil fuels, earth's crust, surface ocean, and intermediate and deep ocean.
Great, so they're all highlighted in blue up here on this screen. And so we have all these places that carbon resides. Which one of those is the biggest?
Earth's crust.
Yeah, pretty significant. Earth's crust has a very large number beside it. What is that number representing? Petagrams. Petagram, what does peta mean? Is that one of the metric prefixes you learned?
No. Is it?
What does it mean? 10 to the 15th. So down here in your legend, it says petagram is 10 to the 15th grams. So just like kilo is 10 to the 3rd, peta happens to be 10 to the 15th. It's not a number you'll see very often, but in a large scale like this, we're talking about the total mass of carbon. It's a valuable number. So what are 3 processes that release carbon into the atmosphere? Are there only 3? There's more than 3, so who wants to list through? Go ahead. Okay, so I'm going to highlight those 3. So you said burning of fossil fuels. What was the second one? Ocean loss and volcanoes. How does carbon get released into the atmosphere? What does that even mean? How does carbon get released into the atmosphere? What does it mean to go into the atmosphere? Eleanor?
Okay, I may be going to. Would there be some sort of chemical reaction to cause it to break up and to go?
So, love it. Love it. So when we're talking about carbon, we're talking about an element. We're talking about atoms of that element. And it's not that that carbon atom sits by itself. Why do we know that carbon doesn't sit by itself?
It has to have 4 bonds. No.
Hopefully everyone in class was thinking the exact same thing. You're like, that's too obvious. No, exactly. Carbon always has 4 bonds. You're not going to see carbon by itself because it's unstable by itself. So the question is, what is carbon surrounded by? And if we're looking at fossil fuels, 1, 2, 3, 4, 5, 6, 7, 8, 9. Go back. 1. This is octane. Have you heard of octane before? Where? Gas stations, right? 93 octane fuel. That's talking about how much of your fossil fuel has a particular hydrocarbon. A compound is composed of 8 carbons and a whole bunch of hydrogens attached to that. That's one of the forms a carbon can have. When we take that and we burn it, what does that carbon then end up as? So this is, what state is this in? When you put it into your car, what state? Is it solid, liquid, or gas? So this is a liquid that doesn't just evaporate by itself and go into the air, mostly because it's underground, right, as a fossil fuel, with a whole bunch of other hydrocarbons. And if we pull out crude oil, it's a mixture of different hydrocarbons. Some of them have 8 carbons long, some have 9, some have 10, some have 20, some have 40. Those heavier ones are used in diesel fuel. Even heavier ones are used to put the tar on your roof, because when you burn them, there's just so many parts that get gunked up. So after we burn this, we combine it with oxygen in your car, right, and it combusts. Where does this carbon atom end up after a combustion reaction? What is it part of? Every one of these carbon atoms, if the reaction's clean and goes like it should, which sometimes it doesn't, but for the most part, we assume that every single one of these carbon atoms is now part of a carbon in CO2. If we have CO2 here in front of us, is it going to be a liquid as well? No. That's a gas. And if we do octane, right, we're going to make 8 carbon dioxides for every 1 octane that we start. So that's what it's trying to get at here. It's saying that there's all these different places that carbon can be, and it's not always in the form of octane. Out here in the plants, it can be in the form of cellulose and like sugars, right? Sugars are these circular structures of carbon. And so these are all different ways that carbon can be. The more atoms are connected together, the more likely it is to be a liquid or even a solid at room temperature. The smaller it is, the fewer atoms. CO2 has only 3 atoms in it, and that's going to be a gas, because it's easier to move into a gaseous phase and not be pulled down by gravity. So then let's take that and run with it. The other processes, let's highlight those real quick. Deforestation, land change. Plant respiration, plants breathe. Is that weird? It's pretty weird the first time I thought about it. I was like, I guess in the daytime, they take up CO2 and they do respiration, or they do photosynthesis. But at night, they don't have any sun, so they breathe. They basically do the same thing that we do. So we have, I think those are the main ones, right? In the oceans, CO2 dissolves into the ocean, but it also can come back out. And so that's kind of what that in and out of the ocean is. All right, so then what about question 18? Describe a path for carbon to reach the soil after a fossil fuel is burned. How can I do that? Describe in more detail, Dylan.
Photosynthesis.
So just maybe a sentence instead of single phrases?
Because when the plants, of course, they get the carbon out of the atmosphere.
So the plants take this CO2 out of the atmosphere, goes into this channel there in photosynthesis, and then it goes into these plants. But then how does it reach the soil from there?
I mean, it's not really, freshed up on the process, but I mean, there's carbon in the plants. I don't know if a lot of it stays within them or if it continues to go back into the soil. Either way, it goes into the soil, whether the plants do it themselves or if they die.
So the plants have carbon in the form of, after photosynthesis, it's in the form of carbohydrates. So that's the simple, like, condensed formula, but usually it's like sugar. All right, and there's rings of carbon. So it takes carbon that's attached to oxygen and breaks them apart, chemical reactions. Builds cellulose out of these sugars. And then these, when the plant dies or the leaves fall, what happens to them? That's what this litter fall is referring to. So the litter fall, those leaves fall, plants die, and then they end up sitting on top of the earth, they decompose, and a lot of that gets put down into the soil. So that's one of the paths.
And some of the rivers take some of that.
Rivers take some of that into the ocean. That becomes sediment down here. There's other forms of sediment too. Okay? So why is this diagram, or other versions of this diagram, called the carbon cycle?
It never ends because of the masses. So for energy.
Don't jump too far. So Jessica, do you want to add to that?
It all goes at, ends up going back to the same place. Like it start here, goes up and down, and then it goes back down.
Great, so if we burn plants, goes up into the atmosphere. In theory, plants will take it back up. It'll go back down, or it'll be taken up here. And so all these kind of are different processes that can either take carbon, make it a gas, CO2, or that CO2 can get taken up and can become a whole bunch of different things once it's taken up by plants or the ocean. And so that cycle means that the carbon is kind of fixed. So what do we say then about, given what we learned about the conservation of mass within a balanced chemical equation, do you expect that there would be any overall loss or gain in the carbon cycle? John Paul, what are you thinking? Can you speak up, John Paul? You want to pass?
I never raised my hand for a reason.
All right, who wants to help us tie this back together with gain or loss of carbon? Okay.
It's the cycle, so I would think it wouldn't gain or lose, it would always be balanced.
Always be, I don't know if I'm going to use the word balanced at this point yet. We'll come back to that. Chris?
It's the fact that there's no carbon being taken like out of like the entire Earth, so there might be like displacement of carbon in different places at different times, but there's never going to be like, carbon that's just taken out of the Earth and placed somewhere else.
Great. So if we think about the Earth as kind of this closed system for all the atoms that we have on the planet. If you zoom way out and you look at our atmosphere, it's this really thin little layer around the Earth, and there's very little that ever escapes that because gravity keeps pulling it back in. So the question is the carbon going to be in the soil, in the crust of the Earth, in the ocean, or in fossil fuels, or sediment, all these other places, or is it going to be in the atmosphere? It's not one or the other or out of here, right? So it has to be in one of those places. It's a closed system, it's a cycle, and so when we talk about balanced, I just want to be careful we're not saying that it's always going to have the same distribution between the atmosphere and the soil. So what plays a factor in what the ratio is in different places? Season, yeah, temperatures change, and the ocean, if it's warmer, will hold less gas, and it puts it back into the atmosphere. What else can influence where the carbon is found?
We're burning it and we're not replacing it back into the earth.
So if we increase this, and then there's not as many plants to do photosynthesis, that changes that balance slightly. What else? Plants are pretty quick, though, so in theory, if we replanted everything right away, we could pull all that carbon that we burned from deforestation out. Is that true of every... There are some cows on here. Cows eat the plants. So the cows do release another gas, methane, into the atmosphere that's really, really bad. But there's one thing I want to focus on. So this fossil fuel here, we can burn trees all day long and we can replant them, and in theory we can grow it back in 10 or 20 years, right? They're not going to be the same trees. But we can put that carbon back into the earth, into a solid form. Can we do that for fossil fuels?
No.
Why?
It takes thousands of years.
Millions. So this process of going down takes 1 million plus years. How long do you think it will take from the time we started using oil until we run out of it? Running out is kind of an extreme. We're probably never going to use all of it up because it's hard to get to. But it's going to be maybe 100 years, a few hundred years. And so this is kind of where the big concern is right now on our planet, is that we're actually increasing deforestation. We're increasing usage of this. So that means it tips the balance to much more being in the atmosphere than anywhere else. Which is not a problem if it didn't create a kind of blanket around the Earth that kept trapped heat in. So we'll talk more about climate change kind of throughout the semester, but that's kind of where it comes into this conservation of mass. That mass isn't created or destroyed. The number of atoms aren't created or destroyed. They're just moved chemically from one compound to the other. So let's go ahead and flip the page. Let's work on the exercises. I want everyone to complete activity 1. If you finish, keep going. I'm going to come check back in on a couple questions for each question. Exercise 1, 2, and we'll kind of go through like that. So please flag one of us down. You do have a full team in here tonight to help. So we'll be happy to come around and make sure you're moving forward. That was our hand. Oh, I erased the first exam, not the second one yet, so I'll go do that. We're going to try to report out for exercise 1 in about 3 minutes. Alright, so I have question 1E. I guess that bottom of the reactants. What is the mass in AMU of all the reactants? Go ahead and click that answer when you have that.
We need to type in AMU or just the number.
It's numeric, so it won't let you. But I'm glad that you're thinking about it.
Because like when I was doing the homework, I was like, just put in the things, then I went back and circled it and like put it in. Oh, it's screen protected.
Yeah, wouldn't that make it?
Oh, yeah.
You know, so night we was talking to the exam, and I told you I told you that.
Because it said like how many I used to add them all up. I guess it's
See, I was understanding.
All right, we have 33 responses. We getting close? So I'm just asking for the bottom of the reactants column. What is the mass and AMU of all the reactant atoms? And you can guess what the next question is going to be. 39. We're getting close. All right, I'm going to go ahead and close this out so we can see the responses. You might want to hit a 1 if you wanted to submit something, but you can. Participation.
Just like you see a bunch of.
But you didn't. Okay. So we have 2 responses. It's always hard to see with this thing.
They put a 1. That's cute.
So half of our class thinks it's around 88 AMU. I'm not quite sure what the other half of the class thinks. It's hard to see. Oh, just different sig figs. Okay. So then let's go ahead. And next question is, what is the mass and AMU of all the products? Appropriate number?
Oh no.
No, it's all based off whatever periodic table you have. So as many sig figs as you have in your periodic table. All right, a couple more seconds. Even if you had not answered the first question yet, should you be able to answer the second one?
Yes.
Based off of what I showed, if those answers were right, what would you answer for the second one? Why would we answer the same thing?
It's conservation of mass.
Can I get someone to raise their hand to volunteer to explain why those 2 numbers would be the same? Carmen, go ahead, nice and loud.
Because the equation was balanced, so that means that the reactants and products was the same on both sides, so the answer would be the same.
So the mass would be the same before and after the reaction as well.
Yes.
Okay, so many things, but you touched on a couple of them. Equations mean we're not creating or destroying reactants, or we're not creating or destroying elements or atoms, which is the definition of balanced. We don't lose or gain mass. All right, go ahead and do question number 2. And it's going to be very similar. Once we get to question number 3, we're going to talk some about question number 3. Does the atom itself is not molecule.
It's there. Yes. So I can use this part. So it'll be easier for me to just like.
Oh, wait. Yes, it is. No, it is.
It is kind of nice to write it out. Because it's oh, crap. We just talked about that.
It's just a ratio. So like, it shouldn't need to have the same amount of. No, it has the same amount. Oh, yeah. Similar to that, it doesn't have to have the same amount. No. It has to. Because otherwise you're losing carbon.
Okay, so count all the carbon in this one.
It's 2 moles of carbon, right?
Yeah,
It's 2 moles of carbon.
Yeah, check it out. So it'll be 2 moles of carbon, 2 moles. Or every two moles of this one, then you get 2 moles of this one.
And then there's 6. Actually, oh wait, more than that.
There's one out there.
Yeah, eventually.
Wait, that's 5?
They had to be sorry.
That's why I volunteered.
Oh,
2 oxygen, 6 oxygen, 1 oxygen, 4 oxygen. So check that out.
all of these check out.
The moles themselves the moles themselves, okay, because the equation is just a ratio, it still is the same. So you still have 2 moles of carbon. On either side.
The moles depend. Of course, that's how make that computer just like when you graduate, you just blow it up. So then you realize, yeah,
Are the moles of molecules Are the moles of
Yeah, but that's not right.
zero.
plants is literally just like the same thing. It's just like if you had a mold of carbon, it would just be yeah. So like it's we had well, if you had a mold of carbon, it would be
Okay, you're fine. I'm tired.
So that's
Okay, I'll change it. The wording is very, like,
12 grams. Okay, good. That means like you had like 2 moles of carbon. That was the molar mass of carbon. No, it's not the moles.
yeah.
Well, 2 moles.
So we're going to touch on a couple of points of comparison between questions 1 and 2. The first one is it uses this strange term. Are the molecules balanced in this equation? What is it talking about? What does it mean when it's talking about the molecules being balanced? What does it mean when the atoms are balanced? Let's start there. Tony?
They're the same on both sides.
What's the same on both sides?
The number.
The number of them is the same on both sides. So if we say the molecules are balanced, they're implying that are the number of molecules on both sides the same? Dustin's shaking her head pretty vigorously. No. Okay? Sometimes you might strangely end up with the same number of starting material molecules as product molecules, but that is not a requirement at all. That is happenstance. So if we have a chemical reaction, a lot of people when they learn about this, they accidentally say, oh, you have to have, if we have 4 starting molecules, you have to have 4 ending molecules, and that's not true at all. So we're balancing the number of atoms that you start with and you end with. We're balancing the weight because you have the same things before and after, the same atoms, then they have the same weight before and after. You just have different connections between them. And then the last part is charge. So we balance the charge before and after as well. There's one big difference between the last row in both of these tables. The top one specifically says, provide the total mass in AMU of the reactants and products. 2E says, provide the total mass in grams of the moles of atoms in row 3 of the table below. Why is one in AMU and the other one in grams? Talk to your neighbor, make sure that you have an answer, even if your answer is, I have no idea. Tell your neighbor what you think the answer is to why 1 is in AMU and 2 is in grams. All right, would anyone like to share what they discussed in their group? Why is it that one's in AMU and the other one's in grams? Go ahead, Andrew.
Is it because we're dealing in moles?
So make that into a sentence that compares the two.
So since we're dealing with moles of atoms, which is a huge number, putting that in AMU would, it'd be a huge number, right? So it's easier to write in grams rather than AMU.
Great, and so if I can kind of elaborate on what Andrew is saying, the first one is talking about individual molecules and having a few atoms of each carbon and oxygen before and after. If we have a few atoms, we can talk about it in the weight that's really small called AMUs. The second one talks about moles, huge numbers of them. So if you have a mole or 2 moles of carbon to start with, we're not going to talk about moles in terms of a really, really, really small mass unit called AMU. We're going to use grams instead. So for the top one, are we talking about atomic, molecular weight? Would we use molecular weight for the top one, or would we use molar mass? molecular weight for the top one because it's AMU per molecule. And the bottom one, we're going to use molar mass because it's grams per mole. Okay, so let's do question 3. Go ahead and work through question 3 if you have not already.
We weren't doing
I didn't click it in.
We weren't having to, if you wanted to grams, you have to divide it by 1.06.
If you use the molar mass, then you don't need to do that. There's already been. But the difference is the top one you're saying, what are the AMU it weighs per atom? The second one is what is the grams it weighs per mole.
So we're not thinking about the other grams.
So that's how you convert between AMU and grams. But if you have to consider the mole. A mole of things is 6.022 times 10 to the 23rd of them.
I don't think I just, okay.
And the top one is just saying you have an atom versus you have a mole of atoms. Basically, you have so many of them. That's about right.
So this is right. So this should be.
Let me get the balance at first.
Raise your hand if you need another minute to finish question 3A. 3A. Okay. So we're working on question 3A. Keep going if you finish. If you're struggling a little bit or want a little assistance, raise your hand, please. It should be a red flag.
Exactly. That's okay. That's what I was
Try to balance that. Yeah, looks like the right process. I don't have the numbers worked out, but looks like a good
I
set.
just want to make sure before I left it. I didn't know.
Good job.
Bless you again. Look, are you allergic to me?
Okay, let's go ahead and talk through question 3A.
It keeps kicking me out of class.
Because we have 20 minutes left of class, and I want to shift gears in a second, and we're going to be working on that thing I handed out. So if we're going to answer this question, what's our first step? What do we need to do first?
Balance the equation.
Balance the equation. Are all the coefficients 1? Are we good?
No.
Nope. What coefficient do we need to change? Dylan?
HF, 2 moles of that.
2 moles of HF. Anything else?
Oh yeah, you want me to answer HCl? Yes.
Yes.
Yes, 2 moles of HCl.
2 moles of HCl. Does that look right? Okay, so if we look through, we have the same number of hydrogens, chlorines, carbons, and fluorines on both sides of the equation. So we have a balanced chemical equation. So then 3A says, if 2 moles of HF react, how many moles of HCCl3 are formed? How do we answer that? Are consumed. Sorry, did I say produced? I can read. 1. So if we use up 2 of these, 2 moles, is that what it says? How do we know that we're going to use 1 mole of this? So based on the molar ratio. So we could say 2 moles of HF. And if we want to see the ratio between the 2 reactants, we can say that every 2 HF, 2 moles of HF, consume also 1 mole of HCCl3. What's kind of cool about a balanced chemical equation is that we have literally 3, in this case, we have 3 conversion factors we can use. If we want to know how much of the HCl we're going to produce, we know that that's a 2 to 2 mole conversion factor. Or if we want to know how many moles of HCF2Cl, we do a 2 to 1 molar ratio. If we're doing this, can we say, let's say that we started with 10, let's do a different number. Let's do, if we start with 2 grams of HF, does that mean that we will make 2 grams of HCl? Talk to your neighbor. Does that mean if we start with 2 grams of HF, we're going to end up making also 2 grams of HCl? All right, can I have a volunteer? What do we think about 2 grams of HF generating 2 grams of HCl? Sebastian, what did you all discuss? Love it. So one is talking about how many moles. One is talking about how heavy, which is grams. And so having you won't have necessarily the same number of grams of starting material and product. The only way that would happen is if your molar mass was the same of each. Basically saying if they're each the same weight. Then you have the same number of them, and that's really what matters. So what I think we're going to do is we're going to switch gears, and we're going to start working on the handout that I did today. The rest of that packet is really good practice for balancing of equations. That's exactly the kind of thing you should take to office hours, work in groups on, bring to your study sessions with your LAs, or study on your own. So we're going to go ahead and switch to the single page worksheet that I have. And I may or may not have these questions in there properly. So go ahead and work on question number 1. Try to think on your own for a little bit. If you're totally stuck and the people around you can't help, then flag one of us down.
Number 1?
It's number 3.
No, it's number 1. I'm going to move these things around because I changed the questions. So we're not clicking it in yet. Work on the question on your sheet. Those are the right questions.
The number 1 on the sheet?
Correct. Number 1 on the sheet. All right. Slides have been corrected to match your handout.
So guys, on number 1, it says hydrogen disulfide. The actual formula is right, it's just the name of it was wrong. It's just
My brain.
Squeeze. Okay. So, what makes you saying you have some heat in this? How much is it? You know the way this, the way this. How do you figure out? Oh no, that was a 2.
Okay, that. So once you balance it.
Start working on it. And then figure out where
Oh, which one I forget? Oh, crap.
Okay, we're going to take about 2 more minutes and try to write a process down, and then we'll work through it together to make sure we're on the same page, and we'll kind of move forward.
Yeah.
Disconnected me from our session.
Oh, did it freeze?
I think I'm back in.
So how do y'all feel about we start working through this? When we look at a question like this, there are a lot of steps. And it's really, really, really important that we kind of figure out a process that works for us, but that we don't memorize the process. We think about what we need to do and compare. I have a lot of students that will memorize these 4 steps, but then we ask a slightly different question, and you end up totally back where you started and have no idea where to go. So if we see a question like this, what's the absolute first thing we need to do? We need to make sure that it's a balanced chemical equation. So to do that, are there any coefficients that we need to add?
Yes.
All right, can I have a volunteer that helps? Jay? What coefficients did you have?
I have, the first one is nothing, and then the,
First one is 1.
I'm sorry, it's 1. And then it's 6 for HCl, and then it's 2 for FeCl3, and then it's 3 for H2S.
Does anyone disagree with that? We okay with that? Okay, so does that mean now that if we start with 1 gram of Fe2S3, we're going to make 3 grams of H2S? Why can't we make that comparison? Because they have different weights. And so we can say, well, if I know how many of them, I can make that comparison, but not just by the mass alone. So how do I figure out how many of that reactant I have? So this is one where you have to figure out our starting quantity is this guy on the far left. We're trying to find the mass of the one on the far right. So let's go ahead and start with 26 grams of iron sulfide. And how do I go from how heavy to how many? Let's go from grams to moles of the molar mass. So 1 mole of Fe2S3 weighs how much? How many grams does that weigh?
You got that?
What'd you get?
Is that right?
207.88.
Okay, I did
We use the pen publication.
It's probably one where I should have done the math ahead of time and looked it up. But I'm going to focus on the process going forward. Is this close? Is this ballpark? Depending on the periodic table, you should get a very close value. It should only differ to probably the 10th place or so, but around 208. Okay, so if we stopped our calculations right now, we would have said, this is how heavy the starting material is, and now we converted it to how many there are. If we know how many we have, can we then figure out how many we can create of the products? How do we do that? What is the ratio between Fe2S3 and H2S? So for every 1 mole of Fe2S3, we will generate at most 1 mole or 3 moles of H2S. So that means however many moles we found in this first calculation, we have 3 times that many moles of H2S. So can we stop our calculations? Are we done? We need to figure out how heavy. So we now need to go from number of them back to how heavy. How do we calculate how do we convert to how heavy they are? So every 1 mole of H2S weighs how many grams? We go back and look through the conversions we did. We started over here going from mass of Fe to S3. And I should have Fe to S3 down here. To how many in moles. And then how many moles of iron 3 sulfide to how many moles of H2S. Based on the ratio of how many you start with to how many you end with of the reactants and products. And then we can convert from the number of moles of how many to how heavy. How do we feel about this? Okay, so about what numeric value do we have? Can I have a response?
Do you base it on the 26? How do you base it? If you say 12.8, would you base it your significant figures on the 26 and just do 13?
So we have two significant figures. That's how much we start with. These we don't limit our sig figs by. So we base it off the starting value.
So would it be? If it was 12.
So this is a process that, if I can get everyone's attention for a minute, this is a process that applies forwards and backwards. Like I was saying earlier, if we knew how much product we needed to make, we could just do the reverse to find how much of these we would need to start with. The next question that I have is, what is the volume of hydrogen disulfide produced in the previous question? Does anyone know how to go from, let's say the answer was 12 grams of H2S. Any idea how to go from how heavy it is to how much space it takes up? Because if you remember that last problem, this is a gas. Ankar?
Do you need to know density first?
So density is for liquids. You can kind of refer to that for gases as well, and that's a bit of a different thing.
1 gram is 1 milliliter.
For water. But here's something that's kind of a little tip-off for next week. You're going to start your gas laws lab next week. And check this out. If you're at standard temperature and pressure, standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. If we're at those conditions, 1 mole of any gas occupies 22.414 liters.
What do you mean when you said the
1
1 atmosphere?
atmosphere, that's what we have right now at sea level. It's 1 atmosphere of pressure. That's how much air pressure there is around us. So if we're at regular conditions, which we call standard temperature and pressure, then this statement holds true. What's really crazy is it doesn't matter how heavy the molecule is, how light it is, how big it is. If we have the same quantity of molecules of gas, then it's going to have the same volume. So how could we use this in our last question? Or could we use this in our last question? So I don't know if I can go back in. So if we go back to this question, did it let me? Didn't go back, did it? Current project. Go to this one. Why is it not loading? It's not loading. Okay. What I want us to think about is with that last question that we had with the volume. Remember we went through a few steps to find the number of moles of our H2S product? And then the last step was how heavy is it? Instead of saying how heavy, we can now use another conversion factor. So I think the last step right before it was 3 moles of H2S for every 1 mole of Fe2S3. Instead of going to how heavy, we could say that I know that every 1 mole of a gas at standard temperature pressure is 22.414 liters. So your lab next week is going to be looking at how much product you generate in a reaction, but you're not going to be able to weigh it because it's a gas. So you have to figure out, based on the volume that I collect, we could do a backwards version of this. If I know I have 22.4 liters and I'm at standard temperature and pressure, I know I generated 1 mole of gas. And then with that 1 mole of gas, we could then figure out what it is based on a number of other factors. So I wanted to put out that as an additional conversion factor we'll use. Go ahead and try to work through the rest of these questions if you can. There's also a lot of homework problems that will build you up to being able to do this. We may touch on this briefly at the beginning of the week next week, but then we're going to be moving into some gas laws and some net ionic equations.